Hello everyone, welcome to this other round of presentation of MLOps 2021. This year we have so many speakers and I really hope you are enjoying this event like me. My name is Nadia and I work at Nylas as a senior machine learning engineer. Today I'm honored to be here and to have the opportunity to introduce two of our amazing speakers. Before starting, I would like to remind you that if you have a question, please post it in the chat. I will collect all the questions and ask them directly to our speakers after the presentation. So let's start. Our speakers are Navdeep Gill and Michelle Tanko. Navid is a lead data scientist team lead at H2O.ai, where he leads efforts around responsible AI and previously focused on GPU accelerated machine learning, automated machine learning, and the core H2O3 platform. Prior to joining H2O.ai, Navid worked at Cisco, focusing on data science and software development. Before that, Navid was a researcher analyst in several neuroscience labs at the following institutions: California State University, University of California, and Smith Kettlewell Eye Research Institute. Navid graduated from California State University with a Master of Science in Computational Statistics, a Bachelor of Science in Statistics, and a Bachelor of Art in Psychology, with a minor in Mathematics. Michelle, instead, is a data scientist and product manager of the AI App Store at H2O.ai. Her background is in pure math and computer science, and she's passionate about applying these skills to answer real world questions. When not coding or thinking of analytics, Michelle can be found hanging out with her dog or rocking out with the band. Please join me in welcoming Navdeep Gill and Michelle Tanko.
Hi, thank you for that great introduction. Yeah, it looks like we actually lost Navdeep, who tested the screen share. So I am going to go ahead and kick us off until he joins us back so we don't have to wait for too long. I think he might be having some internet problems. So I need just a moment to pull the slides up since he was going to do the screen share. And it's not going to be fully zoomed at first, but we'll just go ahead and get started. All right, so today Navdeep and I will be talking about doing security audits for machine learning attacks. We'll be going over why you would want to think about machine learning attacks, some different types of ways that machine learning models could be compromised, and some general concerns and solutions for these types of attacks. And then we'll wrap up with a summary of our work. All right, so why would there be machine learning attacks for models? A majority of time, there are specific types of people, whether this is malicious insiders, hackers, or associates, that may want to use machine learning models, which are running as an API to gain information about how the model works, to steal inside information or business rules, to infiltrate corporate entities, this could be corporate espionage, and to understand and access intellectual property. So we'll first go ahead and talk through some of the types of attacks. So one of the first attacks we're going to mention is data poisoning. So what is data poisoning? Data poisoning is when a hacker or malicious insider somehow accesses unauthorized training data of a model. So this could be data which either... Sorry, I just got a message from Navdeep. I'm seeing he's going to be joining us yet. All right, back to data poisoning. So essentially, this is a way that data is actually altered before the model training, evaluation, or retraining process. The reason this is a problem is because the original data to build the model has actually been altered, and so the model can't be trusted on new data and could be making predictions that help some malicious entity get value from the company, but not actually help the customers or solve the problems that is intended to be solved when you're actually building the model. So essentially, this could be a small company where one person is allowed to access both training data, production data, or deployment data. Because one person does a lot of jobs, this could be a malicious insider, or at a large company where someone is able to, say, do hacking. So how does it actually work? Well, the original clean data, when it built a model, there might have been predictions that were, say, in this case, someone should be denied or approved a credit card or loan. But by altering the data, the predictions change. So the data and the model can work exactly how the malicious attack, the attacker was planning for it to work, without actually being the original how the data would have trained a model on its own. This gives the attacker inside knowledge into how the model works and allows them to exploit this weakness in the model. So what can you do to have defenses for this type of attack? Well, there's a couple different types of analysis that you can run both on your data and on your models. So in a post hoc model analysis, you could run disparate impact analysis. So the idea behind disparate impact analysis is to understand if your model is treating different groups within the data unfairly or differently. So if you were to imagine a model that is predicting if someone should be approved or denied a credit card, we would want to know if it was making predictions differently based on protected classes like gender or race. When you run disparate impact analysis in general and you find any classes which are being treated differently, this could be a sign that maybe data had been altered. You can also use special types of models which are specifically built for fair lending or for understanding that the model will treat different groups appropriately. We could also look at doing residual analysis. So essentially, when you look at the predictions from your model, digging in and understanding if there's any unusual behavior in the residuals, if there are specific anomalies in the data or in predictions that maybe are different than you would expect. So some of these processes are manual and would take a human to understand, looking at the data and navigating to see if something looked unusual or not. The next type of attack we'll look at is backdoors and watermarks. So in this type of attack, hackers are able to infiltrate the production scoring system. Or again, there could be malicious actors inside the organization. How this works is that we're able, sorry, just one moment. I'm going to actually let Navdeep talk about this when he comes back, and we're going to jump over watermarks and go straight into surrogate model inversions. So with the surrogate model inversion attack, for anyone who's not familiar with the machine learning practice of surrogate models, essentially this is where you build a predictive model that tries to take training data and predict predictions. So the reason this could be a malicious hacker or attack is that if you had a public API for your model, say it's running as a REST server or a REST endpoint, and users are able to send data and get predictions, they could actually send simulated or fake data to your model and get predictions. They would then be able to take that fake data and the predictions and build their own model that would predict what your model predicted. So essentially, it's trying to understand how your model works. This is bad for a couple reasons. One, it can expose proprietary business logic. So if you're able to build a surrogate model that follows certain rules to make predictions, users and hackers' competitors could understand how your proprietary model is working. It also can reveal sensitive information on the training data. So by understanding how different rows of fake data get different types of predictions, users can understand what your actual data looks like. And then this is actually step one of two attacks we're going to talk about further. This would be membership inference and adversarial. But first, let's look at how surrogate model inversion attacks actually work. So essentially, some organizations, when they deploy a model, this might be running in some sort of publicly accessible manner because end users would want to be able to score or use the model. So this is, in this case, we're looking at a simple decision tree, but this could be a model that's running as an REST endpoint or otherwise, where users send data and they get back predictions. So essentially, a hacker is able to simulate data, send it to the model, and get back predictions. And then they use that as a training data to build their own machine learning model that predicts what your model would do. And so this is how the attack would go ahead and work. All right, I think Navdeep has joined us back, so I'm going to finish up surrogate models and then I'll hand it back to him for watermarks. So what can you do to defend against a surrogate model inversion attack? The main thing would be authentication and making sure that only users that should be able to use your model are able to. So there may be some reasons we would want a model running as a public API, but ensuring that only the appropriate end users are able to send data and retrieve predictions would be the best way to prevent against this type of attack. Other things you could do is add watermarks to data so you can understand where data is coming from and what predictions are. So watermarks within data are going to be similar to a physical watermark, such as in dollar bills or on proprietary physical copies of paper, where you can see that the data is coming where you know what the data is coming and marked in a special way. This would be a way to know if new data was coming in, did not have that mark. There's also things you can do in a model operations side, which can limit this type of attack without fully stopping it if for some reason authentication wasn't an appropriate solution. And this would be throttling. There could be simple rules in place where if you see a single endpoint is using your model a lot all at once, you could reduce the amount of information that they're about to, or that they're able to get from your model. This would give security or IT teams time to look at that case and understand if it was appropriate or not. So by throttling the amount of predictions the hacker is able to get, your team has time to understand if it is a hacker or not. Another thing we can do is actually a white hat exercise of building your own surrogate models and understanding what you can glean from your data. So if you're able to build a surrogate model and learn information about your training data, this gives you insight saying that maybe someone who's malicious could as well. So I'm going to go ahead and stop. Navdeep, we went through everything but watermarks, and I will give it back to you.
You guys see the screen now?
Yes, we can.
Okay.
Great.
Yeah, so yes, now we're talking about backdoors and watermarks. Essentially what these are is, so the backdoor is obvious. So there could be a hacker who infiltrates your production scoring system, or there's people in your organization, which sounds unfortunate, but you know, it is possible. It's not impossible. And essentially what they're doing is they can change the scoring mechanism of your predictive modeling system to react to some watermark data, which you could think of as, you know, a unique set of information that a hacker can send to your predictive modeling system through some API or through some online interface or anything like that. And then once the backdoor is exposed and it understands what this unique set of information is, it can respond back with whatever the hacker wanted to respond back with. So they would have embedded some response that they want from this predictive modeling system once they've hacked it. Now, so here's like sort of like a visual example. So you can see we have the original model, and here it says, you know, the hacker added a backdoor to the model scoring mechanism, and then it's exploited with watermark data to get some favorability involved. So in this case, you see they have this variable YOJ, so a user can try to pass in that type of information that they put in the backdoor, and then it will come back with, say, approve or deny, depending upon what they're trying to infiltrate. So this is something that can definitely happen. It's you know, it's common in probably software as well. Typical software, you can add in backdoors, or you can add in other ways to sort of get into a system. The same applies to a machine learning system as well. So some defenses you can do. So you can do some type of anomaly detection. So you can look for any anomalies that are coming into your predictive modeling system, things that don't make sense, observations that don't make sense, input that doesn't make sense. You can use anomaly detection to sort of look for these things and hopefully mitigate before anything detrimental happens to your organization. There's also data integrity constraints. So typically someone does ETL or something like that, there is some expectation as to what the data should look like based off of some analysis that you've done or some subject matter expertise you have. The same can be applied when you're deploying a predictive modeling system. Data is coming in, your system should have some expectations as to what this data will contain. So for example, let's say someone put in how much money they make in a year, and they sent you, I don't know, $100 billion. I mean, that's probably an issue, and you should probably handle that or figure out a way to handle that. You can also do disparate inputs, which is a way just to see if there's any disproportionate treatment of observations across your modeling system. So this can help also detect any type of watermarks or anything like that. And the final thing is, version control of your scoring code. So as long as you can keep, version control of your scoring code and see what happens, that's pretty much a pretty good way to sort of keep track of this, because the backdoor is going to be, well, obviously the backdoor won't be added this way since it would be too obvious, but it is good to have version control in general, and it might help detect any odd behavior that's happening with your system. So I think that's it for that. And then I think, Michelle, you went over the model inversion attack.
Yeah, we can jump right to membership. So
here is a membership inference attack. So this is related back to the model inversion, but it's sort of a two-stage attack. And usually it happens, just like most of these things, due to lack of security or some type of distributed attack on your model API. So just like I said, the first stage is you do a surrogate model inversion attack. So that's where you basically get the data by hitting an API, and you're able to get back information with the predictions, and you also know what you inputted. So you're basically constructing a data set at that point. So that's what you get from the surrogate model inversion attack. Now there's a second level surrogate model, and this is trained to discriminate between rows of data that were in the data set you were able to generate, or were not in the data set you generated. So this is the data set used for that surrogate model from the first bullet point. So obviously this will reveal what types of data is used or is in your data set versus not in your data set. And simply knowing that type of information, you can gain things about individuals. So you're automatically in violation of privacy or group privacy or individual privacy. And essentially, if this attack is carried out to its extent, you can actually rebuild sensitive training data. And that's obviously a concern, because privacy is very important nowadays. It's a concern across many industries, so social media or anything like that. Information is collected all the time, and we sort of trust these systems to, I guess, keep it to themselves. But in this case, they can obviously be exposed with this type of attack. So here is a visual of the previous attack that I was talking about. So you see step one, you train the surrogate model to obtain the potential training data with the predictions. And then you can make also sort of another column in there called in train to decipher if a row was in the training set or not. And then essentially, once you have that, you can train the second level surrogate model to discriminate between rows in your training data and not in your training data. So this is sort of a visual of what I was just explaining before. Now the defenses, so we can reference back to slide 12 here. So all of these still apply from the model inversion attack, because this is the first step. And then the second step is you want to sort of monitor your training data that's being used. So you want to make sure that the data you're seeing that's coming in sort of resembles the data used to train your model. And you also want to ensure that the real-time scoring are very similar or somewhat similar to the training, validation, and testing. And if not, they should be recorded and sort of mitigated at that point. And Michelle, you didn't go over this either, correct?
No, we'll do that now. So
Okay.
About membership inference, which is sort of a step 2 to the surrogate model attack. But we also, please keep sharing your screen, Navdeep.
There we go.
Thank you. But there's another attack that can happen in tandem with the surrogate model inversion, and that's adversarial examples. So essentially, we have the same setup. There is a lack of security around a specific model, or someone inside the company is able to use a model that maybe they shouldn't, and they send slightly altered data rows to understand how to change a specific row to get different predictions. So this allows the hacker to understand your proprietary business logic and also how to game your model to get what they want out of it. So if this was a model that was approving or denying some sort of event, they would learn exactly what they had to do to the data to get the approval they may want. We can also oh, perfect. Yes. So this is exactly what this looks like. You have your model. It's running as some sort of API, or it's internal to a company and a malicious data to it. And a training data set is created not just of sample data, but of sample data where each row is slightly different from the next one. So if you're able to see on this tiny screen, we had our first row, which was sent to the model, and it had a high probability of denial. The next row only changed one column, the next row changed another column, and essentially we're seeing how changing the data changes the prediction. By the 7th try, we found that if the delinquent number was a negative number or a really high negative number, our likelihood of deny actually went down to almost 0. And so our hacker is able to understand that this is a specific rule in our model, that this delinquent is a really important column and this value of it. So they're able to steal the logic there and also set up new data to game the system how they might want to. So how can we actually help prevent this? And there's a question in the chat about this. So some of the defenses are similar to the ones we've done so far. You can look for anomaly detection. That is, you should be analyzing your scoring or testing data set as it comes in to see if any of the testing data rows are very, very different than normal. You can also ensure model has authentication, so users are only able to access it if they're supposed to. But if for some reason you have a malicious actor that's able to actually use your model when you're not expecting them to, this is where model monitoring can be really important. So essentially, anytime a model is used in production, you would want to understand and have a list of rules that give alerts for strange behavior. This could be something like, we just got a bunch of rows in a row that were slightly different from each other, looking at similarity of the different rows that come in. If for some reason you have a malicious actor that's using your model, there's not authentication, and you're not able to stop an attack from happening, what can be really helpful to do is your own attempted hacking attack. So a white hat, either sensitivity analysis or surrogate models, which we talked about earlier. So if someone were to do this attack on your model, what information would they be able to glean from it? So essentially, you would build a training data set where you slightly alter different rows and understand how predictions change for that.
Okay, great.
Great.
So I can go on. So yeah, we just talked about adversarial examples. So the next attack, which is called impersonation attacks. It's I think from the name of it, it's pretty straightforward. So in this case, the hackers or the bad actors, they learn through inversion or adversarial attacks the attributes that are favorable to them by your model, and then they try to sort of impersonate that. And you can do it just by what I just mentioned here. It's just sort of playing with the model and figuring out what gives the favorable outcome. And then you'll also do it by disparate impact analysis, basically trying to figure out what group of people is the privileged class. And then if you impersonate the privileged class, you will get the favorable outcome that you want. So those are a couple ways someone can do an impersonation attack. Like before, we have sort of a visual. So, there's an original model, there's a set of data coming in, and you can see here the person who's inputting data into the model. This is sort of a credit example, and you see month delinquent is 1. The attacker who has a month delinquent of 4 can see, oh, if I just do 1, I can probably get the favorable outcome I want because the probability of deny for this person is only 0.25. So they will get sort of, in this case, whatever they're looking for, whether it be a credit increase or a loan or anything like that. Through this impersonation attack, they can get something from the model that they would normally not get. And then sort of defenses for this is just like most of these attacks, as long as you have some type of authentication, you can sort of defend yourself against impersonation attacks. You can also do disparate impact analysis, which is a very important thing in general. But in this case, deciphering or figuring out if you don't have any privileged classes or able to decrease the bias can prevent this impersonation type of attack as well, based off the second bullet point I mentioned, where they can use disparate impact, figure out the privileged class, and then just mimic them. And the third step, which is also very common across these type of attacks when it comes to defense, is look for very similar predictions that your model's outputting, and also look out for very similar input that's coming in. You could imagine if someone's constantly hitting your model with the same type of information to get the favorable outcome, this would show up in real time, and then you can sort of mitigate that and take care of that. I didn't mention it here, but previously there was mention of throttling. This would technically work here as well. So we've sort of gone over the types of attacks that your machine learning system can be hit with. And then in this slide, I just want to go over some general concerns. So the first one is black box models. So a black box model basically is a model that's hard to interpret inherently. So something where the model needs some post hoc type of tooling to actually figure out what it's doing. Now, the issue with this is your hacker can actually learn more about the black box model than you can, based off of just their hacking exercises and based off the fact that it's a black box model. So if they do their due diligence, they might actually learn more about what the model is doing and hence exploit these attacks. There's also this concept of black hat explainable AI. So explainable AI enables human learning from machine learning, regulatory compliance, and automated decision, but it can also make ML hacks easier and more damaging as well, because you're, in this case, the actor itself is using these explanation techniques to sort of gain information based off of surrogate inversion or anything like that. So that's another concern that you should consider as well. And of course, there's general concerns like DDoS attacks, which is common in regular software systems. So you would obviously take that into account as well. Anytime you have distributed systems or models, I guess you could say the attack surface is a lot bigger. So anytime you have data or code spread over many machines, there's more of a surface for attacks. And then the last one is package dependencies. So as most of you know, a lot of ML pipelines are most likely dependent on some type of the package from the open source. The issue with this is if you were able to get a package from the open source, that package itself can contain something that can, sort of hack into your system. They could have something built in that sort of attacks your system. So making sure you keep your dependencies in line with what has worked or what you vetted is very important, and you should continue that process as you move forward when it comes to adding more dependencies. And then here's a list of just general solutions. So authentication is probably one of the most important ones. If you can prevent your prediction API from being hit, hundreds or thousands of times, you can probably take care of a lot of these attacks by the mere fact you're shutting them out. The next one is you want to sort of have benchmark models, so you can compare complex model predictions to less complex. And for traditional data mining problems, the predictions shouldn't be that different. And if they are, you probably need to do some investigation. But the idea of benchmark models are very good because you might have a black box model versus sort of this white box model. And if the prediction accuracy is not that different, you should stick with the white box model. It will sort of save you in these type of attacks, and it's also just more interpretable in general, which will, make your life a lot easier. And also there's some type of, you can do some type of encryption or differential privacy or federated training to sort of ensure that the data you're using or anything like that is sort of kept private and it's not exposed or has the potential to be exposed. And this last bullet point kind of goes back to what I mentioned in benchmark models. Try to use interpretable models and fair models. If you can avoid black box models, that should definitely be something you strive for. A lot of times, I think in most cases, the white box model will perform just as well or just not as different as the black box model itself. And there's plenty out there. So here we mentioned you could use monotonic GBMs. There's obviously rule fit. There's GA2M, GAMs, GLMs. All these models are interpretable, and they can probably do just as well as a black box model on tabular data, which are usually still one of the highest use cases you see in industry. So general solutions, continued is model documentation, management, and monitoring. So all three of these play a big key component in ML security. The model documentation, is sort of about taking an inventory of what you've done in terms of modeling, and document and if you document it well enough, then whoever's investigating can figure out easily if what they're seeing is vastly different than what has been documented. Having these things in line will make the mitigation effort a lot easier, and you'll be able to respond a lot faster. So once you're able to put this in line, that's pretty good. And also, the documentation will also reveal who or what group of people were involved in making this model. The next thing is model debugging and testing. So, you always want to test your models for accuracy, fairness, and privacy before you deploy them. You can do white hat surrogate models and apply explainable AI techniques to them to see what hackers can see. So just like I mentioned before, the surrogate inversion one with the surrogate inversion, you can get your training data and predictions, and then they can use XAI techniques to interpret what they're seeing even more so to gain more information. So that's something you should try before you deploy as well. Just try some white hat surrogate models, hacking type of exercise, and see what you can uncover, and then take the steps to mitigate that in the future. And system monitoring, model monitoring is also something you should keep in line. This will sort of help with seeing how many predictions are actually being sent out in a period of time. You look at latency, CPU, memory, and disk loads. And then essentially what you're using this for is to look for any type of anomalies that are coming into your system. So this is not just specific to ML monitoring. I mean, specific to any type of software that you deploy in any type of system. These are things you should definitely be looking for. So in summary, I should mention that ML hacking is currently still probably rare and exotic, but as ML becomes more prominent, this will potentially become an issue as well. It's the same concept with traditional software. Software started picking up, people started using it more, then obviously it became bigger and bigger, and then all of a sudden the potential to get hacked started to exist. So the same thing can happen for ML modeling systems. You should be aware of insider threats. It's definitely possible that there could be malicious actors within your organization as well, depending upon what type of problems you're facing or anything like that. And anytime you have open or public prediction APIs, they can be kind of a nightmare for privacy and security. So a lot of the methods we mentioned before will definitely help with that, but you have to do your due diligence when it comes to these type of prediction APIs. And then, there's also ways for people to just sort of try to hack into your model and game it to steal, steal your proprietary knowledge or your predictive models as well. So you should try to keep in line with some type of license agreements or terms of service to sort of prohibit this, especially if your competitors are trying to do it as well. And then, of course, just having overall best practices around IT, security, model management, and model monitoring will just help in general. with a lot of these things. And I should mention that with ML security, it doesn't just involve, data scientists or people in analytics. It's a group effort, just like I mentioned in the last bullet points, IT, people doing model management, model monitoring. You can imagine in a big organization, this is spread across many people. So it's always good to keep in line with everyone and everyone's team to make sure that these attacks do not become part of your reality in the future. And with that said, that's the end of the talk. This presentation is available at this link. And there's also some references here that I suggest you go through. They go through a lot of these things that we've spoken about in much more detail. And these are just the references in general about basically pointing to papers mostly. And that's it.
Thank you so much to both of you for the very informative presentation. I suggest maybe if you can share the link directly in the chat so people can directly access them instead of copying. It would be really great. We usually
I did already. Yeah.
Awesome. Thank you so much. Okay, so I see 3 questions. So I'll start from the first one. What kind of work is H2O doing in privacy preserving machine learning?
Oh, so I can answer that. Yeah, so when it comes to security, privacy, machine learning, H2O itself is basically acting as a sort of consulting with customers per se. So this is things that the team I work on pretty much does. We have been looking at how to add in some type of, I guess, software solutions, or I've been looking at in general. What I'm thinking about it is it would most likely be some type of tooling. So it won't be a sort of just like you just turn it on and it does something for you. It's a tooling exercise. The ML security is all about running proper exercises. So you see that with software security. You usually, as a program, you throw in your jar or whatever you want to use, and it sort of runs through an analysis and gives you a report. You can imagine the same concept with ML security. So this has been what we have discussed at H2O, or specifically on the team that I'm on. That's what we discussed.
Thank you so much for your answer. Okay, I'll move to the next one. Can you elaborate on broader attack surface hindering forensics effort toward deep learning, federated learning, probably, solutions?
Sorry, can you repeat that question?
Yes. Can you elaborate on the broader attack surface hindering forensics effort for deep learning, federated learning solutions?
The DP is going to be differential privacy. There's an update in the chat. Thanks for that.
Okay. So is it just basically talking about the around broader attack surface? Okay. So imagine if, let's say I deploy some ML system, right? And let's say I deploy it on my laptop. The attack surface will be my laptop for the most part. That's where I'm running everything. That's the IP that people are hitting to get their prediction. Now imagine if I did a distributed deployment of this. Let's say I just had, I don't know, I'm at some social media company. I have billions and billions of data points. Obviously, I probably need to deploy it across many clusters to deal with latency and all these type of things. Now the attack surface has become a lot bigger. There's more things to account for. There's different subsystems at play. There's different people at play who are probably helping you with the distributed part, the people making the algorithms. There's people setting up the servers. If it's in the cloud, you have people working on the cloud. The attack surface has just gotten astronomically bigger. So there's more things to account for. That's what I was basically talking about there. So a lot of times people probably don't even have big enough data to do that. So they can sort of avoid it. But, obviously if you're at a social media company or any of these bigger, FANG companies, then it becomes a problem. And then you sort of have to consider this. The attack surface has gotten bigger at that point.
Okay, thank you so much. And apologize for don't reading the question well. No. And we do have the last question. So how can we achieve model privacy with that you just mentioned?
So the main way to achieve model privacy would be, simply put, so we presented you with sort of things you can do for model privacy, things you can do to sort of cover up sensitive information, things you can do to prevent data being leaked through your model. all of these attacks, if you see the solutions and the attacks themselves, they all have to do with exploiting information about your users or whoever is involved in dealing with your modeling system. That's what it has to do with. So all of these methods themselves involve just due diligence. I mean, that's what they involve. There's not a a quick solution that you can deploy. You're taking all these to account, and you're making out some exercise that your team can follow. It's just like if someone wants to, let's say you're in cybersecurity, there's a lot of times there's engineers there who are just involved in bounties. They're just looking for things. They're basically hackers, but they're on the good side, not the bad side. And they're trying to figure out, is there anything that I can exploit? If I can exploit it, then someone who's a black hacker, black hat hacker can sort of take advantage as well. So that's something you should try to do. It's just about due diligence. It's just about having the proper mechanisms in your organization to avoid these pitfalls. And yeah, that's the key. And you see these across many organizations for many different topics. For example, in finance, you have fair lending. They have mechanisms to do everything before they deploy a model. So like I said, that same concept can be deployed or employed in your ML security pipeline. That's all it really takes. And just like all machine learning, it's due diligence, making sure everything's up to standard.
Awesome. Thank you so much for your answer. Okay, so I don't see any other question coming, only just some comments about the answer. And yeah, it seems we are good to go. So thank you so much, guys. I really enjoy your presentation. Thank you so much for being here and to participate to ML Ops. And I hope you have all a great evening.
Great. Thank you so much for having us.
Thanks, Nadia. Thanks, everyone.
Bye.